Hello everyone. So today we will discuss Python again. This will be our second session. We'll continue from where we left off in the first session. So if you remember, in the first session we made a basic 5G interactive tool in which we got some inputs from the user and we provided the peak output throughput for that configuration. So if you remember, let's quickly do a recap. So in this case we were taking bandwidth, subcarrier spacing and MIMO layers, and then from bandwidth and subcarrier spacing we were counting the number of resource blocks, and then in the end we were multiplying them together through this equation where number of PRBs were multiplied with the transport block size. This is a static value that we got before by calculation into the slots, into the MIMO layers, divided by 1000 into 1000, so to convert it into megabits per second, and we got an output throughput. So this is how it looked like. We put the bandwidth as 100, subcarrier spacing as 30, MIMO layers as 4, so it gave us that available number of PRBs, physical resource blocks, is 273, while the maximum throughput for this configuration is 1707 megabits per second or 1.7 Gbps, right? So now this is the initial version that we had, but this one is not really realistic because it gives us the peak throughput, while in reality most of the users will be all over the cell. They will be indoors, they will be in weak coverage, medium coverage, so they will have different throughput values, and a very few number of users will actually be having the highest peak throughput. So for a realistic 5G tool, we should find out a tool that can give us throughput for all of these users. So if we want to find throughput for a user that is in bad coverage, we should get that as well. So it's open to the user. Whichever kind of throughput or whichever kind of user throughput he wants to find out, he should be able to do that. So let's have a look how we can do that. So for instance, this is the same MCS table that we discussed last time. MCS table can go from 0 to 31, but the maximum value that we can use is 27. The last 4 are reserved. So for 27, the maximum number of spectral efficiency is 7.4063. That means 7.4063 bits per symbol. So this is the value that we are using in the current code to get the maximum peak throughput. But in reality, we cannot get this throughput all the time. For instance, if you look at this user which is near the cell, so it gets MCS 27, which is this one, so it gets a peak throughput. But a user which is, let's say, a bit far away in the medium radio conditions, so he will get a lower MCS, for instance MCS 19. So for this one you can see the spectral efficiency is 5.11, which is lower than 7.4, so it will get a lower throughput. For the same scenario, if there's a user which is indoors will have more losses because of the indoor losses, the wall losses, the building penetration losses, so it will have a lower MCS, let's say MCS 11. So MCS 11, we can say that bits per symbol is equal to 2.7, so it will be more lesser compared to MCS 19. Similarly, if a user is in very poor condition, then he will get much more poorer MCS. In that case, let's say MCS is 3, so it will only give us 0.877 bits per symbol. So that means it will have a much lesser throughput. So in this case, we can find out that for different scenarios, a different MCS will be allocated. So in order to get the throughput for different scenarios, we will have to incorporate this MCS table in our code. Now how to do that? This is where the concept of list comes into play. So we will create a list. Let's say I put that list here. Let's start a new list. So because it gives me spectral efficiency, so I say spectral efficiency MCS is equal to this. Now this will be my list. Now I've already copied this table out in text format here, so I'll copy all of this, see, and I will paste it in my code over here. So if you see here, we have now a list. Each of this value indicates the value over here in the spectral efficiency from the 3GPP table. Okay, so and they are separated by a comma. So each comma indicates that this is the next value in the list. And if you remember, the last value, the highest one, is 7.4063, which we are currently using. Now, if you might ask, where are we using this 7.4063 in the code? So let me also remind you that if you remember over here, we were calculating this 977 bits, which we are using over here in the code, in the equation to calculate the throughput. And this 977 is coming by multiplying this value 7.4063, which is coming from this table MCS27 7.4063 into 132, and 132 is coming from the total resource elements that we have for data, which are the blue resource elements, which are the PDSCH resource elements. If you remember, we have 11 symbols for PDSCH. If you count these blue symbols, 11, and we have 12 subcarriers in one resource block. So 12 into 11 is equal to 132. So this one, 977 bits, gives us the transport block size of one resource block using this configuration with the maximum MCS value. So let's also convert that into something that we can use. So let's say I put here TB size is equal to 132 static 7.4063. I think this was the value, 7.4063, and instead of 977, now we can use int TB size. Also, this value will be something in decimal, so it's good to convert it into without decimals, which can use floor, math.floor TB size, and then we can use this TB size in the equation below to get the maximum throughput. So let's just see, verify that the code is still running properly. So let's run it again. We do 100, 30 kilohertz, 4 mass layers. So yeah, so even if we replace the 977 with the TB size that we calculated now, the value is still same. See, the code is still running properly. So this is okay. Now what we need from the user. So we will let the user decide what MCS he wants, right? So for that one, what we can do is this. You can say MCS index is equal to input, enter the MCS index, and we also give the guideline that it should be between 0 to 27, right? And we stop here. So now the user will enter an MCS. It can be 0, 1, 2 up to 27. And how do we ensure that it converts into this value? Now this list shows that it has 27 values because there are 27 MCS, and we copied 27 MCS values over here. So to address each value, for instance, if I want this value, then what I can do is spectral efficiency MCS 0, because this is in position 0, so I can write like this: spectral efficiency MCS value 0. This will actually give the value of this this entity, because this is the on the address location 0 in the list. If I do, let's say 3, then it will give me value, return the value 0, 1, 2, 3, this one. So what I can do here is that I can ask the user to give me an index value. Then if I want that index from here, I can use this one, because whatever he gives me 0, for instance, it will be stored in MCS index. So I copy this, see, and I put it here. So now what will happen is that whenever the user will enter the MCS index that he wants, this will be entered here, and it will reference the value from this list and get me the MCS spectral efficiency. So let's say I want that. So let's say let's initialize another indicator to y is equal to this. We can also print this over here. Print the MCS spectral efficiency is, and we need to print y to see that we are doing it correctly, right? So this is will be here. Now because we are getting the spectral efficiency into y, that instead of using this one, a static value, we can multiply this by y, right? Because y is giving me the MCS value of each of these indicators, and now I can make it work dynamically, right? So maybe I don't need to int it because it's already an integer. Okay, so there you go. Okay, let's see if this works out. Here, enter. We do 100 megahertz, 30 kilohertz, 4. Now first let's try the maximum MCS, which was 27, and see if it works. If you look here, I put the MCS 27, which was the maximum value. So it says the MCS spectral efficiency for MCS 27 is 7.4063, which we already know, because we were using this one before, and the throughput is 1707, which is same as that. So that means the code seems to be working. Now let's try another value. Let's say 100 megahertz. We say 4. Sorry, I made a mistake there. Let me try again. 100. So it was 30 here, 4 here, and now let's say we try 19. Okay, MCS 19. So it tells me the MCS 19, the spectral efficiency is 5.1152. So let's go back and verify this from the table. So MCS 19, and we can see the spectral efficiency 5.1152. So that is correct. And if we go back to throughput, the throughput for this configuration now is 1179. So you see it has reduced from 1707 Mbps to 1179 Mbps. Similarly, let's try something. A user, if it is user is in a very bad conditions, in a very bad radio conditions, so 100, 30. Now in bad radio conditions, the MIMO layers will also reduce. Usually if you are in very bad radio conditions, he will use maybe only one MIMO layer, but let's take 2 for instance, and let's say MCS is 3. So now the MCS index for 3 is giving the spectral efficiency of 0.877. Again, verify from here, MCS 3, and the spectral efficiency is 0.877. So we can say that this is correct as well, and the throughput will be only 100 Mbps. So if for the same scenario we say that only rank or MIMO layer is only 1, then 30, MIMO layer is 1, MCS 3, then we get only 50 Mbps, right? So this just goes on to show that how the MCS will give you a different throughput, and now with this code you can actually find out the throughput for different users in different radio conditions. Now comes the other issue. When you are using a mobile, let's say you have an Android mobile and you want to look at your radio conditions, it's not simple. There are applications for Android where you can get some of the radio parameters for your mobile, but usually the MCS is difficult to get. However, the CQI is easier to get. Now what is CQI? CQI is the channel quality indicator. So it might be a better idea that instead of using MCS for this whole algorithm, we can use CQI as well. Or it can be another idea that we can use both and let the customer choose whether you want to use MCS or you want to use CQI. So let's try that as well. So from the same principle, we have in 3GPP a table for CQI as well, and for each CQI we have the spectral efficiency over here as well. So in the case of MCS, you remember we had lots of MCS indexes from 0 to 31, while in the case of CQI it's only from 0 to 15. So it has a lesser number of indexes, but the idea is similar. For instance, if you want the highest throughput, a user will be in very good conditions, CQI 15 will be used. So CQI 15 is equal to 7.4063, which is similar to what we had in the MCS table. MCS 27 is equal to 7.4063, right? So this is similar to that. Similarly, if a user is in medium conditions, he can use CQI 11, which is, let's say, 5.1152. If he is in a poorer conditions inside the building, CQI 7, which is 2.73. If he is in a very bad condition, in a poor radio condition at cell edge, let's say CQI 3, then it is 0.877. So in the similar concept, we can use the same list concept to make this kind of algorithm as well. So let's say I already have it copied here. I'll paste these CQI and MCS tables in the description of the video as well, so that you don't have to copy it again. So let's make another list now. This time we make a list with let's say we make a list for MCS instead of CQI, sorry. So we do spectral efficiency CQI is equal to this. Now this is the list for CQI. Now in this case, what we can do is that we can ask the user what he wants, right? He can choose CQI or he can choose the MCS itself. So let's say I make another one. Index is equal to input, choose input, zero for CQI and 1 for MCS. So user will now choose if he wants CQI or MCS. Now after he has chosen that, then we put another one. Sorry, let's make this one the choice, because it is a choice, and let's make the next one index. So index, enter the corresponding CQI or MCS index, and we can put here as well for the user's benefit 0 to 15, and this can be 0 to 27, right? So now the user will know that if he chose MCS, he should use from 0 to 27 over here. If he chose CQI, he should choose 0 to 15 over here. So this will be the input. Now we have the values here in choice and in index. So now how to make sure that when the user uses 0, he refers to this table, right? And when he chooses 1, he refers to this table. So for this one, we can use a simple if statement. So let's say we do it like this: if, so choice, if it is equal to 0, then y is equal to, because we know that 0 means CQI, so then y should be equal to the CQI table, right? So we put CQI, C, and what we want here is the index, because this is where the user will enter the index for CQI or MCS. So we use index here. So in this case, what happened now, that if it is choosing, user is choosing 0 for CQI, then the if statement will enter over here, and if it chooses 1, then we can say int choice is equal to 1, then y is equal to, then if it chooses 1, which is MCS, then y should be referring to this table, right? So we should go C, and in this case again the index will still be the same, because that is common for both CQI and MCS. Okay, so here we will have the MCS index. So if the user chooses 0, then this statement will be correct, will be true. User will enter here and it will refer to the CQI table, which is this one. If user chooses 1 here, then user will, this statement will be incorrect and this statement will be true. So user will enter here and we will refer to the MCS table. So in this case, we can correctly find out which one we want, and over here we can remove this one, right? So this is here is out, and we can still print this, but we don't need it anymore because now we have CQI as well. Now if we have this, for instance, then we multiply this with y, we have this value as well, and over here TB size, we have the number of PRBs, so everything should be fine. Let's see, let's try and run this code and see how it looks like. Okay, so bandwidth 100, spacing 30, MIMO 4. Now let's try the MCS one that we already tried before. So enter 1 here and we enter 27 here. So this one looks fine. We got the throughput 1707, which we already know was the maximum throughput. Now let's try CQI. Again, let's do the same configuration and we try CQI with the same configuration. Now here I put 0 for CQI and I want the maximum throughput, so I put 15 because CQI, the maximum value is 15. So we have an error here. Let's quickly see and find out what happened here. Okay, so it says it's out of range, which means that most probably our index is not now out of range. So let's just verify that. Let's quickly see this like this: 100, 30, 4. I use CQI again. This time I use a lower value, so it still works. So it means that the code is working with a lower value. It means that 15 took the value outside the list length. Why this happened? Let me show you. So the list length over here is, we calculate it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. While what we are using, the list length is 16. When we say 15, then it means start from 0. So 15 actually means the 16th element, and in this list the 16th element does not exist. Now why it does not exist? Because of this issue. If you in case of CQI, 0 does not have any value. So in actuality the value starts from 1, which means that 0 to 15 will give us only 15 information elements, or 15 parameters, and not 16. So when I put 15 over there, I was actually referring to the 16th element, which does not exist. So to counter that, what we can do is we can put this value, let's say repeat this value over here. So for CQI 0 or CQI 1, for both the cases the same value will be used. So in this case, let's see. Now if we try the same configuration, I go for CQI, I try 15. Now we get the correct value. So we found the throughput as 1707 Mbps, which is the maximum value that we could look for. So now what we have done here is that we have a code which can be used for both MCS and CQI. So whatever the user has, if the user has CQI value of the mobile, it can use the CQI value to find the throughput. If the user has MCS value, it can use the MCS value to find the throughput, and it can tell us the throughput of all the kind of users that are available in the cell. So now this is much more practical or realistic throughput throughput calculation or throughput tool. Now there's still one more thing that is left. In all the radio environment, we have something which is called block error rate or BLER. So let's understand that concept as well, and we can, if we add that into this, then it will be the perfect tool, a realistic practical tool that we can use wherever we want. So let's say when an E node B or G node B is sending data to the UE, so let's say these are all the subframes. So each subframe is carrying 10 megabits, and there are 10 subframes. So 10 megabits divided by the total volume divided by total time will be our throughput. So 10 megabits per frame, there are 10 frames, so they will be 100 megabits. Total time is 10 seconds. So 100 megabits divided by 10 seconds is equal to 10 Mbps. So in this case, all of them were successfully decoded by the UE. So block error rate is 0. So that is 0%. Now let's look at this one. In this case, what happened is that out of the 10 blocks, 10 subframes, 2 of them were not successfully decoded, or they were NAC'd, negatively acknowledged. So in this case, during these two, we can say nothing was transmitted. Nothing was, because the G node B transmitted it, but the UE could not decode it. So effectively, the value of this is 0. So what happened here is the throughput will be 80 megabits because 2 of them are lost. So 8 subframes, 80 megabits. The time is still 10 seconds. So 80 megabits by 10 seconds is equal to 8 Mbps. And the BLER is, we can say that BLER out of 10, 2 blocks were not acknowledged or were not successfully decoded. So BLER is 2 out of 10 is equal to 0.2 or 20%. So if we know the BLER, then we can estimate the throughput like this. estimated throughput is equal to maximum throughput into 1 minus BLER. So this means if we knew that the maximum throughput here was 10 Mbps, and in this case we knew the BLER was 0.2. So if 10 Mbps into 1 minus 0.2 will make 10 Mbps into 0.8 is equal to 8 Mbps. So if we know what the BLER is and we multiply that with the maximum throughput, then with the 1 minus BLER into maximum throughput, we can estimate the throughput as well. So with this scenario, let's say we can also add one more entity here, which is the BLER. So let's say I say BLER target is equal to input, enter the block error rate percentage. Okay, so if I do this, now the user will know that he also needs to enter a block error rate, and we can just simply put it here using the same formula that we just discussed. So it will look like this: static 100, let me put it as this, 100 minus int BLER target. So now BLER target will be a percentage. Let's say if the user puts in 20%, then 100 minus 20 will be 80, and we need to convert it into 0.8 to actually work out. So what we will do is that we will divide this whole by 100. Let's take the number of it. This is bracket is okay. This bracket is for this one, and we need then I think one more bracket here. Okay, so now this bracket will be for this one. So this one, and this is for this one. Okay, so this is how we can convert it into a BLER based diagram as well. So let's see if this works out. Sorry, I think there should be a bracket. Okay, let's try. We have 100 megahertz, 30 kilohertz, 4. Let's choose MCS. Let's choose 27. Let's choose 20%. So now you see for the same configuration when we were getting 1707, now with 20% BLER we're getting 1365, which is a lower throughput. So let's try the same one with 0% BLER to verify that the code is working fine. So the code with 0% BLER is still the maximum value, which is 1707. So usually the BLER increases when you are in poor radio conditions. So let's have a look at this. Let's try CQI this time. So we do 30 kilohertz because in poor radio conditions we'll only have one MIMO layer, for instance. So we do one MIMO layer. You choose CQI, and then in CQI let's choose CQI 1, which is very low value, and for BLER we put a high value, let's say 17%. Usually anything above 10 to 12% is a high value for BLER. So if you put 17% here, this is high value, so we get only 7.25 Mbps. So the throughput for this condition is, as you can see, very low. So this is how we can find out the throughput for a low value with the BLER as well. So now with this code, what we have done here is that our code now works for multiple users in multiple scenarios: good coverage, bad coverage, medium coverage. Then we also have the flexibility of using MCS or CQI, whatever the user wants to use. And then we also added the block error rate targets. So with that one, we can now find out the most optimum, the most realistic, the most practical throughput a user will get when he will be in different radio conditions. So I hope this one clarified all of your doubts, and I hope that you were able to learn some of the Python and the 5G concepts together. And if you like it, please subscribe and we will continue doing that, and we will move to more advanced concepts about Python and 5G, and we'll discuss how we can make them come together and make more tools like this, and how we can use Python to find out to put intelligence in our optimization tools as well. So best of luck. Do stay tuned. Do like it. Do share with others, and do subscribe. Have a nice day. Bye bye.